This is 40 Days of Chemistry Part 26, this time looking at 9.6.3 and 9.6.4, electrolysis and corrosion protection. And the first thing is electrolytic versus galvanic cells. We studied galvanic cells in 9.2.4 and we know they're spontaneous reactions where a voltage or current is produced, the anode is negative, the cathode is positive. But electrolytic cells are different, they're non-spontaneous reactions and you cause them to happen by applying a voltage or applying a current, and in that case the anode is actually the positive electrode and the cathode is the negative. But everything else stays the same. Electrons go to the cathode, cations go to the cathode, anions go to the anode, red cat, anox, and oil rig all apply, and both require electron transport and ion transport. So how do you figure out electrolysis, cell reactions, and voltage? There's a few steps, or there's 8 steps that we follow, and you should probably know how to do these already, but basically you have to determine which species can actually react. So the first thing you do is which species can be reduced at the cathode. The one with the most positive reduction potential will be the one reduced. The E0 of that reaction will be E0 reduction. Then you determine the species that can be oxidized at the anode. So what species are there at the anode and which ones can be oxidized. The one with the most positive oxidation potential will be oxidized, but don't forget the oxidation reactions have to be reversed and the sign has to be reversed off your standard reduction potential list. And that E0 will be E0 ox. The cell voltage required when you add up E0 reduction and E0 oxidation will be a negative value because this is all about applying energy and you've got to apply more than that voltage. You need to supply more than that voltage to get the electrolysis to occur. The cell reaction, similar to galvanic cell, is the combined reduction oxidation half equations, remembering to balance the electron numbers first. And here's a little challenge for you, a little question here in purple. So think about this question, see if you can answer it. So pause the video, have a go, and press play to check your answer. So the answer I calculated was that you produce hydrogen gas at the cathode, liquid bromine at the anode, and you require more than 1.91 volts for that cell reaction to occur. So what factors affect the actual electrolysis reaction? Well, there's 3 things that affect the actual reaction that takes place. The first one is the electrode material. If the anode is inert, say the anode might be made of stainless steel or graphite or even platinum, that means only the species in solution can be oxidized. If the anode's a reactive metal though, it may be oxidized. You've got to take that into account when you're figuring out your redox reactions at the anode. The cathode metal is always protected from oxidation. It's cathodically protected, but it may become coated with a metal that's been reduced from its ions, and that's called electroplating. So for example, if you put copper in as your cathode inside a silver solution, you get silver depositing on the copper cathode or electroplating on the copper cathode. Electrolyte chemicals are the next thing that can affect what reaction takes place because the species in the electrolyte can be oxidized and reduced, and they determine what reactions happen at the anode and cathode. Electrolyte concentration can also have an effect on what reactions take place, and that's because the E0 values on the standard reduction potential list are only for 1 mole per litre. And if you change electrolyte concentration, that means you might change those E0 values, and that can change which reactions have the most positive reduction potentials. And so, for example, for sodium chloride, when you've got very low concentration of sodium chloride, you get hydrogen being produced at the cathode and oxygen at the anode. At higher concentrations, you still get hydrogen produced at the cathode, but you might get oxygen and chlorine or just chlorine at the anode. And if you go straight to molten sodium chloride, so there's no water, that means you get sodium produced at the cathode and chlorine at the anode. So what factors affect the rate of electrolysis though? And that links to our electrolysis experiment. Now according to Faraday's first law, the amount of substance produced or dissolved depends on the quantity of charge through the cell, and the rate of electrolysis thus should depend on the rate of charge through the cell. And by definition, current is the rate of charge. So the current through the cell determines the rate of electrolysis. And now we know that current flow is determined by electron transport and ion transport is slower, therefore we call it the rate limiting step. So pretty much any factor that's going to increase the rate of ion transport will increase the rate of electrolysis. And from Ohm's law we know that current equals voltage divided by resistance, and thus what can we do to increase the current? Well, the first thing is we're going to increase voltage, and that can increase the current and therefore increase the rate of electrolysis, but also anything that decreases resistance will also increase greater current and therefore increase rate. And the things that affect, or the things that can decrease the resistance, if you decrease electrode spacing, or you increase electrolyte concentration, or if you increase electrode size, they all reduce the resistance to ion motion and therefore that increases the rate of electrolysis. Don't forget, in our experiment we electrolyzed copper sulfate using copper electrodes. The independent variables were all these 4 things we tested above, and we compared them to a control sample. The dependent variable was the rate, and we measured the rate by the mass loss at the anode. The control variables were temperature, and also all the other things that were the independent variable we tested. Safety, looking at chemical safety, copper solutions are irritants, toxic and heavy metals, therefore use gloves, wash hands afterwards, and store for proper disposal. That's the end of 9.6.3 electrolysis, so on to 9.6.4 about shipping materials and corrosion protection. And as far as the history of shipping materials is concerned, there's only a few real materials you've got to worry about, and it's linked to the technology at the time and also the materials that were best for the application. So first of all, they used wood, obviously, because that was available. Once the technology was there to extract copper from its ores and we could make brass and bronze, they started being used in ships. Then when iron was able to be produced, we started using iron because of its strength for nails and eventually the hulls. And eventually, once we could start purifying our iron better and making steel, that took over because it was much stronger, much less brittle, and also less prone to corrosion than iron. But you need to know some reasons and applications for all these things in the history of metals. These days, though, we don't just make ships out of steel, we use other metals as well. But why do we make ships out of steel? Well, because steel is the cheapest, strongest, or best strength to weight ratio material with high toughness out there. It's the optimum material for making structures out of, thus making ships out of. It does have one drawback though, and that is the fact that it corrodes, therefore you need corrosion protection. But even though steel is so good for making the hull of a ship and the motor of the ship, there are some particular applications on shipping where there are other metals that are better, and therefore it's worth spending the expense to make those metals as part of the rolls. And the first one is bronze. Bronze is used in propellers because of its good wear resistance. Brass is used for fittings and decorations due to its pleasing appearance and it's got high corrosion resistance. Copper-nickel alloys are very good at withstanding corrosion, particularly in salt water and at high temperatures. So they're used in the engines, fittings and pipes, particularly if you've got some ships have what's called seawater cooling. The engines are cooled with seawater, and to pump that seawater in and therefore pass around the engine at high temperature, you've got to use copper-nickel alloys. Stainless steel, because of its corrosion resistance, is used in galleys, which is the kitchens, and also used in fittings and railings due to its corrosion resistance. Some vessels also use aluminium, titanium and composites. They're mainly vessels where lightweight is very important, so single-person boats or racing boats where the lightweight can justify the cost. But how do we protect steel against corrosion? We said that steel needs to be protected. Well, one way of protecting steel against corrosion is to basically just remove the reductant or remove steel altogether. And that's because corrosion is a galvanic process. It requires an oxidant, a reductant, electrolyte, and also electron and ion transport. And therefore, if you can remove any of those things, you stop the rusting process. And one way to stop rusting is to just get rid of steel altogether. And we talked about it on a previous slide, showing the metals that can be used to replace steel. But there's there's two other ways of protecting steel, and the first of them is barrier coatings. And a barrier sits on the surface, and it prevents contact between the steel and the oxygen and water, which is the oxidant and electrolyte, therefore preventing corrosion. And probably the most common barrier coating is paint. Paint is cheap, it provides a barrier, but if it's scratched, it no longer provides protection where the scratch is, and you get crevice corrosion under the paint, which is unseen, which is a problem. Rustmaster Pro, though, is a modern paint. It's a complex chemical system. It's designed to react with the surface of steel, producing a chemical layer which doesn't allow ion transport or electron transport, and therefore is very good at preventing rusting. Surface alloying is not painting, but surface alloying is actually bombarding chromium ions into the surface of the steel. That turns the surface into stainless steel. Therefore, the surface where the protection is needed has that chromium oxide passivating layer without the entire structure being full of chromium, and therefore it's cheaper than building a whole structure out of stainless steel. Noble metal coatings. Sometimes these are very useful. For example, tin coating your food tins, and that's because tin is a noble metal. It won't corrode and also won't react with your food. The problem with tin coating is if you scratch the tin, you've now set up a situation where you've got a galvanic cell with iron being the anode, and therefore the iron oxidizes much faster because iron is the more reactive metal out of iron and tin. But then you've got galvanizing coatings, and galvanizing coating is where you coat it with zinc. Now, zinc itself is a passivating metal, even though it's reactive, therefore it corrodes quite slowly, and therefore it provides long-lasting protection. However, if you scratch a galvanized coating and expose the steel, what you've set up now is a galvanic cell where the zinc is the anode and the iron is the cathode, therefore the iron is cathodically protected. So galvanizing is a combination of barrier protection and also cathodic protection. But just be aware that for all paint systems or all coating systems, they require constant maintenance to make sure they're still working, and that means you need to be able to access the structures, and therefore it's not always suitable for all applications, particularly say underground pipelines. Cathodic protection, we touched on this. This is the third type of protection system, and galvanizing is an example of this. And what it is using an electrochemical cell to make iron the cathode so it can't oxidize. We know red cat, reduction occurs at the cathode. If we can make the iron the cathode, it cannot oxidize, therefore cannot corrode. And there's two types. There are galvanic cells, cathodic protection, and also electrolytic cell cathodic protections. And galvanic cell cathodic protection is where you've got a spontaneous reaction. And that's where you've got sacrificial anodes and galvanizing. And what you do is usually have magnesium or zinc or sometimes aluminium, and they're used because they're more reactive than iron, and they're connected with the iron in a galvanic cell, and therefore at the anode those reactive metals will oxidize, and the iron is protected from oxidation, and something will be reduced at the iron. It's not iron ions because there are no iron ions there, but instead you get something like oxygen being reduced at the iron surface. Now, sacrificial anodes can protect an area around them. You need multiple anodes on a ship, for example, but they need to be replaced. You need an electrolyte to complete the cell. Therefore, it only works in, say, wet terrestrial or marine environments. Electrolytic cells, sometimes called impressed current or applied voltage, that's where you have an inert anode connected via a power supply to the hull or the metal you want to be protected. Electrons are supplied to that metal being protected, making it the cathode, and the cathode reaction is just as above here. Say oxygen or water will be reduced at the cathode, and the anode reaction, this is why it can be considered slightly better than sacrificial anodes. Because we've chosen an inert anode, it won't oxidize away. It will last pretty much forever, and some other species will be oxidized. But the whole time, the iron, for example, is being protected from corrosion by cathodic protection. Now, impressed current can be used in inaccessible areas because you can just supply voltage down there. You can get remote monitoring, but you need an electrolyte as above, and you also need a constant power supply. So that's the end of 9.6.3 and 9.6.4. This is our penultimate video. The last one, 9.6.7, should be coming shortly.